So the next speaker is Jordan Feekings, and he is the head of section at Fisheries Technology at DTU Aqua, and he is going to tell us something about visual sensors, AI, and how they are using it in relation to fisheries.
Thanks, Stefan. My name is Jordan Feekings, as Stefan has already said. I'm the head of section for Fisheries Technology. We sit up in Hitchens, up at the DTU campus up there, in behind the MEMAAI at the North Sea Centre. I'll tell you a little bit about some of the work we're doing, try and make commercial fishing more sustainable. So commercial fishing is the act of harvesting the ocean of fish or shellfish for commercial profit. If I can figure out the pointer here. Over there to the left, I can't figure that out. Commercial fishing looks very different from small coastal gill nets that you see out on the west coast here. The one at the bottom there, pulled up on the beach, to large pelagic vessels like Peter Henning here, one of the largest vessels we've had in Denmark, around, I think it was close to 90 meters. So they're very different, targeting a wide range of species using a very wide range of different fishing gears. If we look at these vessels and how they fish, you can divide up the fishing gear into two different segments. So you have passive fishing gears and you have active fishing gears. Passive fishing gears are those that we put out into the water and require that fish actively swim into them. So like this gill net here. Then for the active fishing gears, these are gears like a trawl or a seine that's actually dragged over the seabed, which capture the species that enter them. If we look at these two fleet segments, the active gears, this is Danish at least, is responsible for more than 90% of the total catches in Denmark. The vessels from this fleet segment are typically much larger, and consequently can fish in all areas, as opposed to the passive gears. They're much smaller coastal seagoing vessels. The active component is typically comprised of vessels that have a higher fuel consumption. They consequently have a higher seabed impact, and they have higher unwanted catches. If we look at some of the values from Denmark, the catch value in Denmark from the trawl fleet is about 10 times higher than what you have for the Danish sailing vessels, and much the same for the passive fleet segment as well. What is somewhat different from these two over here is the amount of unwanted or discards that come from trawling, which is considerably higher. We look at this fleet segment in a little bit more detail. It's challenged by seabed impact. So these vessels, or the gears these vessels use, typically go hard on the seabed, dragged over the seabed. There's a lot of resistance in the gears to keep them spread. You have big trawl doors, like what you see here, on either side of the gear to hold it open, and which consequently results in high greenhouse gas emissions from this fleet segment. And because it's covering a large area, you typically end up with high bycatches and unwanted catches mixed amongst your target catch. Then there's also issues regarding things like catch welfare, having fish caught in the net for 5, 6, 7 hours before it's actually brought up onto the vessel. And of course, this is feeding into the public opinion that we see in Denmark at the moment, being quite highly debated around trawling and banning trawling. So what all these fleet segments have in common, Thomas mentioned it, it's a harsh environment out there. There's a lot of water, there's a lot of salt. This is from one of the vessels that we've been working with. You try and get good data from something like that, it becomes quite hard. It's also difficult to know what's going on at the seabed. I'll go into that in a little bit more detail further down the track, but it's also difficult to know what is caught. It's a bit of the Wild West out there. Fishermen, after documenting their landings, they don't really want to document their discards or their unwanted catches. So we don't have very good data on the total catch composition. So within my section, we're looking at trying to address these two challenges. The capture process, so putting cameras on trawls to give us real-time monitoring of what's actually going on during fishing, but also looking at the sorting process. So fully documenting the fishing activities and doing this through the use of electronic monitoring. If you look at the capture process, so fishing for commercial species is largely a blind process. We get good information from the pelagic sector, or the pelagic fleet segment. We're using acoustics. We can see what fish are in the water column, how many there are. We get quite good ideas of the species that they're actually after. When we hit the seabed, you get refraction or refraction from it, so you don't actually get a good understanding of what the species are at the seabed. So it's largely a blind process. Fishermen typically, at least in the net prop fishery, they'll fish for 5 to 6 hours and pull up the gear, and based on what they see in the catch, they'll make a decision whether they should fish in the same area or whether they should try and find new fishing grounds. So this leads to quite a bit of seabed disturbance and fuel consumption with very little information coming in real time that they can actually react on. And consequently, you end up with quite high running costs as well. They're big vessels, they're big gears. So we're trying to change this blind process into a much more data-driven process. So we've gone through with a company called Atlas Meriden and developed this camera system that we can actually place down on a trawl. We mount it in the rear end of the trawl, where it starts to become quite small. The canvas section like that, which is a bit conical, so you actually ensure that it keeps its form. And then we mount the camera within that canvas section and pass this data up to the wheelhouse via a coax cable. So we start to get images that are actually usable. Prior to this, we would end up with putting cameras down on trawls, and we would end up with an image like this, completely useless. It's dark, it's a lot of sediment, it's stirred up from the seabed, and you can't actually see what's going on. So what we've done is go through and actually add this canvas, this green rectangular section here at the right up at the front of the gear. That ensures that it takes the sediment out of the water. And when you actually get back to the rear end of the gear, you actually get very good high quality images that can look something like this. So over here to the left, you have something from the Skagerrak, looking at the mixed demersal fish species. In the middle, you have our shrimp fisheries that we have up also up the Skagerrak, down to several hundred meters. And here you also have Norway lobster, one for my Danish. So we can actually see, we can get clear, consistent images in real time up to the wheelhouse. So we've been able to move this blind process into a much more informed process. Now all of a sudden we can actually start seeing what are the different species we're catching in real time. Are they the right species? Are they the right sizes? We can pass this information up to the vessel, up to the fisherman. He can actually start to use this information and make active decisions. But we can't expect him to sit there and for 5 to 6 hours and start watching these videos. He's got other stuff that he wants to do, daytime television to watch, coffee to drink. So we need to start packing this data into something that is actually usable for him. So we've gone through and, in this example at least, classified them into roundfish, flatfish, nephrops, and others. And we've actually passed it up into a GPS position track. So as he's fishing, he can go along and he can see what he's catching. whether he's catching the right species, and actually make informed decisions on that. So where you see, for example, in the shrimp fishery out here in Skagerrak, they fish for 10 to 12 hours and tow in one direction. If you adopt these kind of technologies, you see that behavior actually starts to change. So this picture here up to the right there is from the Pundalis Jordani fishery from the west coast of the US. And they've actually employed not image sensors like this, but other sensors that give them catch information in real time. And then they've seen large changes in the fish's behavior. And instead of towing in one direction and then taking the gear up, you actually see that when catch rates start to drop, they turn around and they find pockets of the species that they're after. This means that you're reducing your unwanted seabed impacts. You're not fishing where you're not actually catching anything of interest. You're not using a whole bunch of fuel and greenhouse gas emissions being released from that for not catching what you're after. So you're getting a much more directed fishery, a much more economically driven fishery, and a more sustainable fishery. If I'm going too quickly, I've lost anyone, then put your hand up and I'll go back a step. So then we've got what we want, and now we pass it up onto the vessel. Now we actually want to see how we can source this catch. How do we actually go about getting information on the entire catch? And that we can do through what's termed fully documented fisheries. So that refers to where all catches are monitored and recorded, not only those that are documented or written down in the logbooks by the fishermen. This can take place in two ways. So that can take place using physical observers, so people that are employed to go out on fishing vessels and work up the catch and document this unwanted component. For example, some fisheries in the US actually are required to have observers on 100% of their trips, or it can be done using electronic monitoring systems. The goal of this is to ensure better transparency, better accountability, and in the end, sustainability. If we look at an electronic monitoring system, it's comprised of a number of cameras. These can be placed in different parts of the vessel, typically where the catch is brought up and sorted. It can also be placed, for example, at the aft end of the vessel to observe where the gear actually comes up on board to make sure that there's no, modification of the catches going on back there. That all catches are documented. For example, in the gillnet fishery, you get dropouts. So you get harbour porpoise that can drop out on the side of the vessel. So to make sure that we understand, at least for harbour porpoise, we can actually place cameras over the side to try and give us that information. It includes sensors that are placed on the vessel to monitor gear activity. So on the back end of the vessel here, you have the drums, which let out the trawl and bring it back in. So there can be sensors that are placed on that to monitor when the gears are set and retrieved. So we know exactly where the fishing has taken place. And then there's the GPS up on the vessel as well to record the vessel location in real time. End of 2023, the European Commission came out with a new control regulation for fisheries. And in there, it actually specifies from, I believe it's 2028 onwards, that vessels over a given size fishing in fisheries that are deemed high risk are to have cameras mounted. So this shows that the European Commission are actually pushing for having cameras on board in the future. And if we look at how the monitoring of fisheries has developed over the last 15, 20 years, we had VMS come about in the early 2000s. So that's a vessel monitoring system to monitor fishing locations. That was introduced on vessels that were first over 24 meters, then it reduced to 21, 18, 15, and now it's almost all vessels that are required to have those systems. And that you can kind of envisage will be what is the case here for having electronic monitoring on these vessels as well. So it's used to verify catches and discards to make sure there's compliance with the regulations that exist. It's used to monitor bycatch, So these can be unintended bycatch, like harbor porpoise, as I mentioned. It can be used to support sustainable stock assessments to make sure that we get as accurate data feeding into these as possible. Currently, we get quite good estimates on the landings. Unwanted component of the catches are collected by observers from DTU in Denmark that actually go out on board these vessels. There's approximately 0.5% of all trips that are undertaken where we have observers on. So it's very few data we get from our observers, but that's the best estimate we've got until date, until we get something like this on all vessels. And then it gives us increased transparency as well. We start understanding exactly what's being caught, what it looks like, and what the entire catch composition is. And then in the end, we don't need to send our observers out. It's an expensive program. It costs around, I think, 5,000 kroner a day to send an observer out. And that's a requirement by EU. So across the EU, we have observers out every day. So it's an expensive program as part of the data collection framework. And if we can look at modifying that into something that's much more efficient, giving us much better data, we end up with much more accurate feeding into the stock assessments. But it's faced with challenges. Thomas mentioned a few of these. Costs, high installation costs, maintenance costs, and then the review process. So we need, at the moment at least, we're having expert persons sitting, going through this data, trying to identify what that is there. I don't want to be that person doing that. We've got issues with inclusion, so layering of catch. You see here, it's difficult to identify the species, but also identify how big it is. We've got issues with lighting conditions, very difficult lighting, changing throughout the day, changing from vessel to vessel. We have issues with faces and hands, tattoos, these kind of things coming into play. These systems to date are mounted retrospective on the vessels as well, and they're mounted on existing infrastructure. So we end up with variable distances. So the proximity to the catch items which you're trying to observe can be very different as well. So meaning it's quite difficult to see exactly that size of the individual, what species it is. And then we've also got a huge variability in vessel layout. Vessels like these here, to the two to the left, they're two vessels we're working with at the moment, where we have sorting tables, small tables that they're standing and sorting. These look very different from vessel to vessel. And you've got gillnet vessels, and you've got large pelagic vessels, you've got sorting bands, which is the easiest scenario. So that's where a lot of the work has been done on AI and image analysis. The scenarios that we see here become very, very difficult. And then, of course, there's the reluctance from industry. The industry don't see why they should take this on board. They find it that it's an additional layer in the regulation. They've already got a rule book that's quite fat. As a 14-year-old that left school very early on, I don't see how they can actually understand the EU regulations that they're having to abide by, and they're afraid that this is just going to be an extra layer on top of that. So if we look at what's been done to date in this field, there was a large Horizon 2020 project called Smartfish, which started doing a lot of work in this field. This is a video from University of East Anglia, which they went through and looked at the different species that were coming across the Conveyor Belt. And you see the numbers on the left-hand side there increase as it's identified. These data, now this doesn't play, so you have to play it here. The problem with these data is that it's expensive to collect, it's expensive to annotate and species identify, as Thomas said, and then we sit with this on our computers or within our specific research groups. So there is a large lack of publicly available data. Malte and Stefan have collected interesting data, which is now publicly available. But it was a huge effort to collect, correct? Would you want to do it again?
Daniel is not employed anymore. He did, but he hates fish now.
So there needs to be more data sets like this. This is one that Martin, my PhD student that's just finished, has put together as part of his PhD. We've actually gone through and labeled every individual. We've gone through and measured them. We've gone through and pit tagged them. And we've run it across the sorting belt multiple times in different occlusion levels to understand what the individuals are, what species they are, what size they are. So this, he's telling me Friday it'll be available. He's been telling me that for a few months now, so I assume probably this Friday. This data will be available. And the idea is that it can be used by other experts that aren't within our research group to try and train their models and improve the model accuracies so we get more and more people working on these challenges. We've put this together as part of a Horizon Europe project called OptiFish. And in there, we'll actually look at different scenarios. So we've got pelagic scenarios where you've got these dewatering systems. We've got the sorting band scenario, which we've already collected sorting tables. So we start to try and build up data sets, looking at the different vessel layouts. So we can try and have kind of a benchmark data set to start with. Then there's the issue of occlusion. You have species that are sitting on top of each other. So to try and give you an estimate of the size of that individual, it's hard to see when you actually don't see the entire length of it. So what we've gone and done is look at allometric relationships. So looking at the size of the total length of the fish and trying to understand what is the tail height, what is the eye diameter, what is the head length, to try and actually see what the correlations are between these different length measurements, to try and say if we can't see an entire individual, how can we give quite accurate approximation over what that is. But then all of a sudden we can actually try and handle scenarios where we have occlusion, where we can only see the head length. We can maybe identify the species, but not the total length. And now, hopefully, by using these kind of techniques, we can get a step further. I mentioned it before, there's issues with the vessel layout. So this is a large pelagic vessel. It's a dewatering system they have on board. Vessels like that can catch several hundred ton in one trip or one haul even. And then the idea of that is to separate the water from the fish. The fish come over in high volumes at very high speeds, which means it's quite difficult to actually go through and identify what species that catch is actually comprised of. And you've got sorting tables like the top one here, which are looking at issues regarding occlusion, hands in the road, not very good catch opportunities to document the catch. So in this project down here, OptiFish, we're working with a company from the Netherlands that's trying to develop a system to place in the pounder where the catch is actually dumped, to bring up the catch routinely, so you can actually start to see that even if you do have occlusion, you know what the last individual was that has landed there, and consequently you can get better information on what species and what sizes it is. Then you've got vessels which are sorting the catch directly as it comes on board, like this gill netter here at the bottom. They face other challenges. Here you see that the gear gets sorted as it's coming on board, but there's also opportunities for catch to actually drop out over the side before it comes up.
3 minutes.
3 minutes, almost there. So you're faced with different challenges. And this is the same video as you've already seen, but this is to show you that this is the easiest scenario that we're working on, and it's also still faced with different challenges. So we have a huge array of vessels that we're challenged with, each kind of having its own problem that needs to be resolved. What can EM also be used for? It can actually be used if we go about it smartly. to simplify the regulatory framework. We've got a very, very complex fisheries regulation in place. Managers are very good at making rules. They're useless at getting rid of them. So what we've gone through and done is look at the different technical measures that are in play throughout the EU. And in a case study for the Kattegat, looked at what regulations make sense and what regulations we can actually get rid of if we go to this new paradigm of fully documented fisheries. And we saw that 95% of our regulations regarding fishing gears can actually be removed. And that's because we're interested in knowing what's actually taken out of the system and what's being caught. We're not interested in how it's being caught. In theory, you can use a coffee filter if you want. A fisherman doesn't want to use a coffee filter because he doesn't want the small fish. He wants to have as much value of his quota as possible. So he himself will go about optimizing the selectivity of his fishing gear to match the quotas he has available. In doing that, hopefully it should lead to better resource utilization and reduced environmental impacts as well. We can potentially have a much more dynamic stock assessment. Stock assessments are done annually. They're very static. They're based on the survey data that we collect on our research vessels, and they're based on the input data from the fishery. If we can feed this information from the fishery in real time, we can actually get a much more dynamic stock assessment. We can also utilize these data to monitor species distributions. We see species moving further towards the poles as climate changes. So we can actually start understanding how those species are migrating, where they're migrating to. New species coming into Danish waters, we can actually see how do we actually start making use of that species as it enters the Danish waters. And then we can also potentially use this for marine monitoring. If we take the underwater example from the underwater camera, we have a camera that's doing transects regularly throughout the day. If we can mount additional sensors on such a camera, we can have information on salinity, oxygen, turbidity. We can get better information on our hypoxic regions in Danish waters, potentially. We can get better understanding over what the environmental variables are that are influencing the species distributions. So the work we're doing is funded by a few projects. So a couple of European projects, OptiFish and EveryFish, and we have some national projects through the European Maritime Fisheries and Aquaculture Fund.
So, yeah.
Let's go ahead.
So the biggest push or force to enforce this monitoring is EU legislations. EU is known for being the pioneers in ethics and responsible legislations. But do you see any way to convince our hungry nations to adopt this? China, what do you say? I assume they won't be very happy to adopt this as well.
That's a good question. There's a number of different EM providers around the world. One of them that come to mind stem originally from the US and Canada. So you see that there is a push in those fisheries also over there as well. And I think our hungry countries, the US comes to mind. Regarding what's being done in China and these kind of countries, I'm not too aware of what's going on over there. It's an expensive system. So they're still quite expensive. So if you're wanting to adopt these to developing countries, it's also one of the challenges. They're also smaller vessels. It's much more remote. There are solutions that are being developed also for these kind of fisheries. So you have EM providers putting systems on vessels in Mexico. There's a push in Mexico and some of their fisheries to have these systems because they can't actually sell their fisheries or their fish to the US market. They don't have them. So you can also see that it's a political push as well. The problem in Denmark, I see that we've had a yo-yo effect since the early 2000s where you get a fisheries minister that wants it and the next one doesn't, and you get one that wants it, then you get one that doesn't. So you see this continuing yo-yo effect.
Where are we now?
We're at a low ground, I would say, where the fisheries minister doesn't want to actually get rid of it. Fisheries commission saying that this is the way we should go. So he changed it to a voluntary program. But you see that the fishermen's organizations are also starting to see that this is of relevance. They need to actually start collecting these data, and if they don't, someone will define what the system looks like for them. So it's still at the point now where they actually have the chance of being part of that and defining what the system should look like for their members.
What do you want to do? I think it's time for a coffee break. And if you have more questions, then you know where to find it.